Hey guys, today we're going to be talking about insertion sort. Insertion sort is quite an interesting sorting algorithm. Many people compare it to sorting cards because the process is very similar. So let's take a dive in and see how insertion sort would sort this array over here. So first off, insertion sort works in steps. The first thing it would do is start from 4 compared to starting from 0. And how it works is it takes 4 and it compares it to everything before it. So in this case, it would take 4 compared to 7. Since 7 is bigger than 4, it would move 7 up by 1 and move 4 in 7's place. So the new array after the first step would be 4, 7, 8, 3, 2, and 9. When you go to the second step, the iterator would move up by 1. So now we would be looking at 8. It would take 8, compare it to the number before it, which would be 7. Since 8 is bigger than 7, and we already ran the insertion sort algorithm on everything before it, we assume that 7 is the highest number, and since 8 is bigger than 7, we don't need to work on it. So now the iterator moves one more step ahead, and now it moves to 3. And starts comparing it again. Since 3 is smaller than 8, we move 8 up by 1, and we move 8 up by 1, and then 3 would be over here, and 8 would be over here. Then we compare 3 again to the number before it, which would be 7. In this case, 7 is bigger than 3, so we would move the thing again. We would move 7 up by 1 and over here, and move 3 before it. And then we would compare it once more until we get to 0. Over here, we would compare it to 4. Since 4 is bigger than 3, we move 4 up again, getting this, and move 3 down by 1. So now we would have a new array of 3, 4, 7, 8, 4, 7, 8, 2, 9. Alright, so now since we were over here last time, we move up by 1 to 2, and we would go through the same process again, checking against every single number up until we get to a number that is lower than 2. In this case, 2 would go all the way over here, and all of these numbers over here would shift up by 1. Getting a new array of 2, 3, 4, 7, 8, 9. Now we would move the iterator up by 1 more, which would take us to the end of the array at 9. Since 9 is bigger than 8, we would skip our loop, and since this is the last element, we know that the entire array is sorted. And this would be the returned array after insertion sort is complete on the array. Thanks. Alright, now let's take a look at the code for insertion sort. So first off, we're going to start off by defining the function in Python. Def insertion sort. And then this is going to take in a list of numbers. So we can say numbers list of ints. And then it's going to return a list, which is eventually going to be sorted. So the first thing that we do is set up the iterator that goes through the entire loop, or the entire array. So we can start that off by using a for loop, and for I in range 1 to length of numbers. The reason why we start off with I, or the reason why we start off with 1 instead of 0 is because we always want to start with the next one so that we can compare it to the one before it. And if you start off with 0, there's going to be nothing to compare it to, and it's essentially going to be a waste of a step. So it's much more better to just start off with 1. The next thing that we do is we're going to set up a current, which is going to store the value of the current index that we're running the for in. So numbers versus I, and then we're also going to store the index before it in a variable called j. So we're going to do j is equal to I minus 1. So it's going to be the index right before I. And now to iterate for everything before before the current index, we're gonna have to use a while loop. So while, and inside the while we're gonna have two conditions. These are essentially gonna be the conditions to check if the number before is bigger than the current number and if we've reached the end of the list. So we're first going to start off by checking if we've reached the end of the list by checking if j, by making sure that j is always bigger than or equal to 0. And for the second condition, we're going to make sure that the number at index j is bigger than number at j is bigger than the current number, bigger than or equal to the current number. So this should satisfy our sorting and going through every number before it. So for example, if we had 4, 3, 9, and we were at 3, then in the while loop we would check, and j would be over here while I would be over here. So I and then j. So first we would check if j is bigger than or equal to 0, which it would be in this case, and then we would check if the number at j is bigger than the current, which would be 3, 4 and 3 respectively. So 4 is bigger than 3, so this would satisfy this, and then we would go inside the while loop. Inside the while loop is pretty simple. All we're trying to do is just switch or move up the 4 by 1. So we can do that by simply saying numbers at j plus 1, because we're trying to go to the next step, is equal to numbers j. So this would basically switch it up by 1. And then all we have to do is go down by 1 because we're trying to iterate through all the numbers before it. So all we do is j is equal to j minus 1. So now we're done with the while loop, and this should take care of moving all the numbers that are smaller than 3 up by 1. So the last thing that we have to do is move 3 at the very end of wherever we stopped after the while loop. So we would do that by simply doing numbers. And remember, our current number is stored in current, right? So we kept track of that numbers. J minus 1 is equal to current. The reason why we do j minus 1 is because of this condition right here. So this would essentially take j to 0, or this would essentially take j, this should be j plus 1, so this would essentially take j to negative 1 at the very end because j minus 1, and then since j minus negative 1 is not going to satisfy this, the while loop breaks. So we would go down here, but since j is negative 1 and that's not part of the list, or that can't be part of the list, we have to add 1 to it to get to 0. And then we would just change that to current, which would be 3 in this case. And then this would be our return list that is completely sorted. Return numbers. Yeah, that's the code for insertion sort, and it's quite simple, and once you understand it, you get to see like exactly how it works and why it makes sense. The best case time complexity for this is O of n, because insertion sort works with a for loop, so you have to go through every single element. So the best case would just be all of them are sorted. So for example, if it's 1, 2, 3, then insertion sort would go through 1, 2, and 3 individually, and then none of this would run, except none of the while loop would run because it simply wouldn't be true. So you just keep on going to the next thing, the next thing. And then the worst case, so best is equal to O of n, and then the worst case would be O of n squared, as you could have a completely unsorted list, well, like similar to this, where you would need to go back and check against every single element, which would get you the O(n) squared time complexity. That's it. Thank you.
Function merge sort. That takes in a list, a starting index, and an ending index. So first let's check the case where we reach the base case where it's only length 1. Then that would mean the starting or the ending index minus the starting index plus 1 will be less than or equal to 1. So we're basically saying if the pointers are at the same point, it's going to be the base case because it's not going to be multiple values, it's only going to be one. We're going to return the list at this point. And this is the base case that will be going back up the tree when we call it recursively. Next, we're going to be handling the other cases where it's not recursive calls. That would mean we're splitting it in half, and that means we're going to keep track of a midpoint. So let's call this midpoint M, and that will be the starting plus the ending over 2. And that will let us keep track of the center. Now, we're going to be calling merge sort on the left and right. So we will say merge sort, we're going to pass in the list, we're going to pass in the starting index, and because we're taking care of the left, we only want to go up to the midpoint, so we're going to go up to here instead of passing in the end like we did here. This will take care of the left subtree, or subarray. Now we're going to take care of the right one by doing the same thing, but this time when we pass in, instead of start, we're going to be passing the index after the midpoint because we already have the midpoint counted for the left one, all the way up until we reach the end. So now here is where we sort the left, here's where we sort the right. Once we're done sorting the left and right, we're going to be merging them back together. So we're going to be calling merge our list. We want to keep track of the start. We also want to keep track of the middle because we're going to be using that for merging. And we're going to be keeping track of the end. And I will be going over this very shortly. So basically, so far, we've kept track of midpoint. Because we don't have a base case, we want to start here. Because it's not the last one, or last base case. We're going to call the midpoint, merge the left, or sort the left, sort the right, merge both the left and the right. And basically, on our final step, just return our list. Now I'll be going over how to merge the two together and what that would look like. So the merge function is used when we're after our two recursive calls, we're going to be merging it back up. And we're going to be passing in the list, the start, middle, and end indexes. Our goal is to sort them as we're merging back up. So what we're going to want to do first is create a left and a right sort of temporary copies. And we're going to be, in the left, we're creating a copy of all the values from the start up until the middle plus 1, and from the middle plus 1 until the end plus 1. So what we've done now is create two subarrays, or not two, we've created copies of the two subarrays. And then we're going to be creating pointers for each of these, and we're going to be checking using these pointers when we're going to be inserting at that index from the list. So that to 0. Then we're going to also keep track of what part of the list we're inserting, so we're going to need a third pointer, and we're going to call that K, and set it to be the start. So at the start, we're going to check the left and the right, and we're comparing them to be put at where the start is. So the first, we're going to be iterating through this entire subarray copy we've made. So while we still have iterations through our left, and we have iterations through our right, and this is why I wanted to make a second one, because I don't want to refer to the same I or same J. I want them to be two separates we can check. R if the length, or sorry, if the left at I is less than or equal to, because we could have duplicates, the right at the same index, but for the right, we're going to be setting the list at K to be the left, and then that's our iterative step. We're going to the next part of the left. Now, in the other case where the right was actually bigger, we're just gonna be doing the same thing, but we only have to check an else because there's only two options. Otherwise, the list at K, it will be the right at J. It'll be doing J plus plus. And once we've either gone through here or here, we're gonna be going to the next part of K we're inserting, because we don't wanna just overwrite the K we just put in. So we're gonna be iterating through K as well. And it's gonna keep doing this until the sorting works, or it sorts through the whole thing and inserts. However, this isn't sufficient enough because there are cases where we wanna actually go through, keep inserting the remaining sub-elements. I had to erase some of it because I wasn't able to fit them all on the whiteboard, so I wrote them, put the whole merge part that I distributed in this little, represented by this little line here. And we're now gonna check if there are elements left in the left or right subtree, or subarray. So first we're gonna be checking while I, if you remember from our little left index we're keeping, when we made it originally, if it's less than the length of the L, that means there's still elements left, and we're gonna be looping through it. Our list at K will be L at I, iterate I by one, and this time we're gonna be doing K plus one in here. And it will go through the entire left subtree, or array, and pretty much add them to K from there. Now the other case, obviously, we're just gonna do the same thing but for the right. While J less than 11, the right list at K is R at J plus K plus plus. So I've gone ahead and drawn a diagram representing merge sort. We're passing in an array with 3, 7, 8, and 1. And how merge sort implements this is we're going to be dividing by 2 each level we go down. You notice the length of the array is 4, then we have a length of 2, then we have an array of a length of 1. What this means is that we're going through each level and splitting it to the base case in log n time. Now, we also have to consider merging them back together. So our final complexity cannot be log n because we're going to be merging them back together. So for the sorting process, when we merge together, 3 and 7 are already sorted. Here we will be sorting 1 and then 8. And then from the way we used our while loops and our ij iterations, we're going to be inserting them in the order 1, 3, 7, and then 8. And what this means for the overall time complexity, this will take n steps because we have to iterate through each item to put it back, to merge it back together. So if we combine these two, we will get an overall time complexity of n log n. Now if you notice, how it's working is, no matter what happens, we have a size of array 4, 2, 1, 2, back to 4. This would mean that in the worst case, you would still have an O of n log n, which is a far cry better than that O of n squared you would get in cases such as selection sort or insertion sort. And this makes merge sort a very efficient algorithm that's useful for sorting lists.
Okay, I'll be going over quicksort. Quicksort is very similar to merge sort. It's also a divide and conquer algorithm, but it's slightly different in the sense that you choose a pivot point instead of splitting down the middle like merge sort. So first we'll be defining a quicksort function. Sort. And then in the function you pass in the array and then a left and a right pointer for the array. Then, since quicksort is a recursive algorithm, we need a termination condition. For quicksort, this is when the right pointer minus the left pointer plus 1 is less than or equal to 1. Then we set the pivot. The pivot can be set to any element in the array, but for simplicity's sake, we'll be using the rightmost element. And then we'll be setting a left pointer equal to the left index of the array. And you can cut it there. Now that we set the left pointer, we can loop through the array to create a left and right partition for it. So, 4, 5. So we're looping through the array, and if the element that we're looking at is less than the pivot, then it goes in the left partition. So the way we do this is we swap the element that we're looking at with that left pointer. Then we move the left pointer up by 1. And again, this creates 2 partitions of the array for the elements less than the pivot and the elements greater than the pivot. Then what we do next is we put the pivot in between the 2 partitions. So to do that, we swap the element at the left pointer and the element all the way to the right, which, if you remember, that was the pivot. So then what we do is we recursively call this function again and do the same algorithm for both of the partitions. So what this does is it passes in the array, and then the portion of the array that we're going to be looking at is that left partition, which is between that leftmost point and the left pointer -1. And then also we'll be doing the same thing for the right partition of the array. The time complexity for quicksort is best case is O of n log n. This happens when the pivot is chosen in a way that the left partition and right partition are about the same size, and that produces the best case. And the worst case will happen in O of n squared time complexity. And an example of when this might happen is if the array is already sorted, and then if you pick the rightmost element for the pivot point, all the other elements will be less than that. So it'll end up being an n squared time to go through all the elements. And that's it.
We're working with selection sort today, and I'm going to explain to you how it works. First, I have a little diagram of really what we do with selection sort, right? So selection sort is a sorting algorithm used by indexes, right? So here we have our first list, right? And every list has an index that starts with 0. The first value in the list is always 0, not 1. And it was 0, 1, 2, 3, right? And pretty much in selection sort, what you're doing is comparing the next value, seeing if it's smaller than that value. If it is smaller, you make it min. If it's not smaller, then you don't change anything. You go to the next value, right? So here we have 2. We're looking at the next value. It's not min, so we go to the next value. It's not smaller than 2, so we go to 3. It's not smaller than 2. So that's fine, right? And then we go down and we pretty much move the min value to the next index, right? So now min is at 4. We're comparing it to the second index at 6. 4 is still less than 6. So then the min value doesn't change, but then it goes to 3. 3 is less than 4. So now the min value changes, and what happens is we have a new list where 3 and 4 switch places. So now 4 is over here and 3 is over here, and then the min goes to the next index, right? So when the min goes to the next index, now min is at index 2, so 6 has a min value, it compares to 4. 6 is larger than 4, so 4 is a new min value, and they swap places. So then we have another new list, which is a sorted list, which is 2, 3, 4, 6, right? So that's pretty much how selection sort works. This is going to be the code for selection sort. So here you can see I already have the function, like the method written out. So here we have a function called selection sort, right? We're naming it num, and it's a list of integers, and we're returning a list, right? So when doing this, right, you have to start off with a for loop, right? So what we're going to do is for I in range when numbers. So we're pretty much, sorry, not num. Since it's called that. So pretty much what we're doing here is we have the I value, and it's gonna be the whole, I is gonna be associated with the whole range of the index, all the indexes of the index, right? So after doing this, we have to instantiate a variable that's gonna be working with our list, or the indexes of our list, and we're gonna call that min, because we're looking at the min values, or for the min values, min indx, right? And we're gonna make that equal to I. Next we have another for loop, right? Which takes in a j value, so for j in range I plus 1 len numbers. Oh my god, sorry, len num. So pretty much what this is doing is there's a j value, and what that j value is doing is as you can see, you have this list right here. So at first we're starting off with this value, right? But you always want to go to the next value. So what the I plus 1 is doing is going to the next value and assigning it to j, right? Okay, so after this, what we're going to do is we're going to have another if statement, right? So that if statement is going to be if numbers, if num, so num is a list name, I, right? So we're going to have if num I is less than num min underscore index, So here what we're doing is if num I is less than num min underscore index, because you have to remember, so I is the value it's at right now, and min underscore index will pretty much be the new index. So one mistake is this is supposed to be j, because min index is I right now, and we want to compare I with j. So this is supposed to be j, not I, okay? So if num at the index j is less than num a min index, which is I, and what you're gonna do is make the new min index equal to j, right? Okay. So after doing that part, we have to now make the code or do the part of the algorithm where we're swapping the values in place, right? So to do that, it's very simple. What you do is num I num min index equals num min index and then num. So what's pretty much happening here is, so the order that the list is in right now is the I value is before the min index value, right? We're gonna make sure that this equals, so we pretty much swap these two numbers. So the num min index equals num I, right? And to print the outcome of that, or to return it, all we're gonna do is return selection sort, right? So we're gonna return num, right? So what's pretty much happening here is now it's returning the number, and we're gonna keep doing this until the whole list is in order. And if you want to see the output of this, you just print selection sort. Okay, so now we're gonna look back at the runtime for selection sort, right? So there is a best and worst case, but the best and worst case are the same thing. So the best case runtime is O n squared, and the worst case runtime is also O n squared, because no matter what, you can't, whatever the size of the list is, it still has to compare at the index of the list. So no matter what, it's always going to run the same.